Let's do problem number 11. A competitive interaction is described by the Lotka-Volterra competition model right here. We want to find and classify all critical points of the system. So the first thing we're going to do is we're going to find the critical points. Then we're going to find the Jacobian and linearize the system because this is non-linear. From that linearized version, we're going to evaluate the Jacobian, which is the linearized portion of the coefficient matrix of the system. And we're going to look at the trace and determine whether we are here, 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 or here. And then, or determine if we cannot actually classify the points because we're either on this axis, and we would be on this axis if the trace is 0. We would be on this axis if the determinant is 0. And we would be inside here if the trace squared minus 4 times the determinant is less than 0. And inside here is fine, but at the limiting case where the trace squared is equal to 4 times the determinant, then we are not able to describe them. And in that case, we'll go over to calplot and we'll do a phase plot to describe them. So let's go over to Matlab. And in Matlab, I'm going to write chapter 11.4 exercise. What exercise? Exercise 11. Okay. So we're going to clear all output, scroll up, and then here we're going to clear all old variables. Clear all. I'm going to define new symbols, so sims x and y. I'm going to defining the functions because I know later the right-hand side as function, right-hand side of the system as functions, because I know that later I'll need those for the Jacobian. So p of x and y and q of x and y. What are those going to be? Well, we need to remember what they were. So for exercise 11, they were 0.08 times x times 20 minus 0.4 times x minus 0.3 times y. And here we had 0.06 times y times 10 minus 0.1 times y minus 0.3 times x. And now that we have these, and we don't want these to output, so let me just make sure that I wrote them right. 0.08 times x times 20 minus 0.4 times x minus 0.3 times y. And here is 0.06 times y times 10 minus 0.1 times y minus 0.3 times x. Okay, well now that we have this, we're going to find the critical points. So the critical points, they're going to be outputted in xsol, ysol, or that's usually how I call them, but you can call them anything you want. Ysol here. We're going to use the solve command right here. And what do we need to put inside? Well, the equations that we want to solve. So this is the right-hand side, and we know the left-hand side needs to be equal to 0 because these are first-order differential equations, and critical points happen when the slope is 0, which is when the first derivative is 0. Okay, now we need to tell it what to solve for. We want to solve for x and y, and then we put some options like that we only want real solutions and true. Now, this does not fit the window, so I'm going to show you a little trick to, if you put 3 dots and you press enter, you can wrap the command and it'll still be the same command, but you can see it all. And actually I want to do this, but I want to wrap it more evenly. So why don't we wrap it here? 1, 2, 3. There you go. So this is a nice trick. So now that we have our critical points, well, we have the code to find our critical points. We want to classify them. So to classify the critical points, the first thing that we want to do is we want to find the generic Jacobian. So to find the generic Jacobian, what we do is we use the Jacobian command. Say that we're going to call it J. We use the Jacobian command, and the Jacobian command wants the functions, the expressions that you want to change. So in this case, it's going to be P and Q, and then it wants to know what you want to substitute in those P and Q. And I want to substitute X sol and Y sol in those P and Q. And I think, hold on, let me just make sure. I want to substitute actually just X and Y. X and Y, because I want the generic Jacobian. So in this, I want to substitute X and Y after I find the Jacobian, which is going to find basically the derivative of P with respect to X for the first entry, the derivative of P with respect to Y for the second entry, and derivative of Q with respect to X for the second row first column entry for Q, and the derivative of Q with respect to Y for the second row second column for Q. So that's going to give us our generic Jacobian. So let's press Control Enter and let's see what we get. We get 4 critical points. 0, 0 tends to always be a critical point because you can't really have a slope if you're at 0, 0, right? Because everything cancels out. And in the Lotka Volterra, it is always a 0, 0. There's always a 0, 0 critical point. So now we have this, and we found our generic Jacobian. Now let's classify each critical point, or attempt to do so, by evaluating the Jacobian. By evaluating the Jacobian. So we're going to evaluate the Jacobian, and I wonder if I just put J of X, Y, if that'll do it without using the subs command. So X sol 1, Y sol 1, and let's say this is J1. And then we're going to do it for all 4 points. So copy this, paste, paste, and paste. 2, 3, and 4. And here we want 2, 2, 2, 3, 3, 4, 4. So let's see if it does this. I'm not sure. I've never tried it. It actually does. So you don't even need the subs command. This is way cleaner than what I was showing you earlier. So now that we have these, the trace here is going to be negative. So that tells us that these are all stable. J2 to J4 are stable, and this is unstable. These are also the eigen values. So now we can find the determinant of each. Let's find the determinant of each. And so the determinant of J1, we'll call it D1. And then we can use our copy and paste and then change the subscripts to 2, 3, 3, 4, 4. Now I should have put a section right here so that I don't re-execute the whole command. Now we get that this is negative. When a determinant is negative, then we're talking about, when a determinant is negative, what are we talking about? We're talking about a saddle. And how do I know that? Right here, look. Look at this graph. This is the determinant axis. When the determinant is negative, we're talking about a saddle, and we'll confirm that later. Now, when the determinant is positive, so here the determinants are positive, now we have a little bit of a problem here because this is unstable, but is it an unstable spiral or is it an unstable node? So in order to do that, let's also calculate the traces. And if we calculate the traces, how do we indicate this? Well, we have to specify J11, J2 of 1, 1, for example, for this entry, because it's the first row, first column. So to find the traces, we can say T1 is equal to J1, 1, 1 plus J1, 2, 2. We're adding these two together. The traces is always the diagonal, so I can also use copy and paste here, and then 2, and I have to change the subscripts, 2, 2, 3, 3, 3, 4, 4, 4. We don't want to change the stuff in here because we're always looking at the first row, first column, second row, second column. So now that we have this, we can actually calculate distinguishing between spiral and not. And how do we do that? Well, we want to see if T1 squared want to see if that is equal, less than, or more than 4 times D1. And again, we can use the copy and paste command here. Put T2, T3, T4. 2, 3, and 4. So now that we do that, we press Control Enter. Oh, I keep forgetting to put a line break. So now we get, hey, this, we have that this is bigger than this. This is bigger than this, and this is bigger than this. So in 3 cases out of 4, this is bigger than this. What does that mean? Well, if you bring this to the right side, this happens when this is bigger than this. So we are talking about unstable node or stable nodes. So for example, we look at the first one. The first one was unstable, unstable, and then we look at this, and this tells us that for D1, where's D1? This is D1. This is unstable. This is an unstable node. D2 is going to be a stable. I remember all the other ones were stable. So these were stable. Stable node, stable node. This one, we don't know. Now, a faster maybe way to do it, to classify them, would have been, and I didn't want to do that. A faster way to classify them would have been to simply, from this, simply find the eigenvalues. So let's say this was eigen 1, eigen 2, eigen 3, and eigen 4. And to find it, we just have to put this command in. So let me do that real quick. So then you just get the eigen vectors, and then you say, hey, look, this eigenvectors are positive, so it's going to be non-spiraling because there's no imaginary component. In none of these there's imaginary components. So we could have excluded that region, this region, from the beginning. So I think this is maybe a more powerful way to do it. Now let's go over to CalcPlot real quick, and let's actually input all this stuff in and see if we get confirmation. So let's go to the vector field, and here I'm going to get 0.08x times 20 minus 0.4x minus 0.3y, and here we get 0.06 times y times 10 minus 0.1y minus 0.3x, and that's 0. Now we're going to say, well, show differential equations notation. Use fixed length for all vectors. And then let's put more vectors in. 15 here and 15 here. And I wonder if I did something wrong, because I'm not seeing any of the points that that we found. So let's see. 0.08 times x times 20 minus 0.4 minus 0.3y, and this one. And 0.06 times y times 10 minus 0.1 y minus 0.3x. And that is 0. Now we have these. Let's zoom in a little bit. And it looks like we're only getting an unstable point here, because what we found was that these were the unstable points. So 0, 0, 50. Oh, maybe the window's not big enough. 0, 0. Let's plot them. 0, 0, 50, 0. 0, 0. Well, I'm not going to plot that one because that's the origin. The other one's going to be 50, 0. So 50 on my x, 0 on my y, and 0 on my... And that's not in there yet because we have to change the window. We'll say that this point, we'll make this red. This point right here is going to be 20 and 40. So 20 here and 40 here and 0 here. And we'll make this color right here. And then we'll put another point in. And that's going to be the point 0 and 100. So the point 0 and 100 and 0. And I want this to be, let's say I want it this color. So now let's bring out the window. Oh, now we start to see some stuff. Now we start to see some stuff right here. Maybe we want more arrows to have a little bit more definition. So let's say we want 25 and 25 arrows here. Now we see we have our critical points here. Maybe you want to zoom in. Well, if we zoom in, then we might want a little bit more arrows. So let's say 35 and 35 arrows. Now we have these critical points. This one definitely looks like an unstable critical point. This looks like it's stable. You see how it's attracting any trajectory close to it. And we said that that was stable, right? This is 0, 100, which is the fourth one. The fourth one has eigenvalues that are both negative. Now let's look at this point right here. This point looks like a saddle. So it should have one eigenvalue that's positive and one that's negative. And this is this point right here. It's the point 2040. So 2040, if we go over here, that was the third one. Third one has these two eigenvalues. See, one is negative, one is positive. So you're able to say that that's a saddle. And this one right here looks like it's a stable point, and there is no spiral. So it's just going to be stable. and that's the point 0, 100. So we should have two negative eigenvalues for 0, 100, which is the fourth point, two negative eigenvalues, which makes me think that this one was not that point, but it was 50, 0. So 50, 0, that was the second one. And we also see that the second one has both negative eigenvalues. So I hope this was useful, and I'll see you next time.